So the separation properties are basically used to classify spaces based on how like topological spaces based on like how, like, very vaguely speaking, how much you can separate the points in that space. And the reason I say how much is because the higher the higher the number, so you have like T1, T2, T3, the stronger the property, which means that like T3 implies T2 and T2 implies T1 and so on. And so I'm not actually sure what like T3, T4, and all of the higher level ones are used for. But I do know that the Hausdorff, I guess, property is useful because it's very it's kind of like how do I phrase this? It's kind of meant to resemble like Euclidean space, if that makes sense. Where like if you think about the like T2 axiom, it seems like something very intuitive in Euclidean space. I don't actually know if it was motivated specifically by like Euclidean space or maybe metric spaces, but that's just the impression I get. And I don't actually know what T4 and T5 are. I did see like T3 in the video because I watched the beginning of it. But yeah, there are actually some like pretty interesting things about T2. Like there's some pretty interesting things you can prove with T2. One of them being that any sequence converges to at most one point in T2.
Oh, yeah.
There's another property. Let me try to find it real quick. It has to do with extending continuous functions between two spaces. Give me a sec.
Yeah, not sure.
You can talk about something else in the meantime if you want.
Yeah. So basically what you're trying to say is that T2 is there to console our intuition, pretty much. So
what's
topology,
not to console is just to generalize it.
Yeah, sure. Like it is the moment where we can finally say, okay, limits make sense intuitively now, and other things kind of make more sense than before.
Yeah, I think there's also something interesting to the way they kind of progress, and I don't know why they progress the way they do, like why the separation axioms progress the way they do. Maybe it's just a matter of like people, just happen to need like different properties for like different things that they were working on, and then they realized in hindsight that oh, this is actually like a stronger version of this, and this is a stronger version of that. But
well, what about?
I'm pretty sure. Yeah.
What about what they were doing, or at least the impression I get is that what they would do is they'd test themselves to add more and more structure, and they would see if the new spaces they create, if you can have a homeomorphism between the two spaces. And if you can have a homeomorphism between them, then they're still classified under the same T. But then if you add like a little bit more structure or something, topological spaces with different properties don't have homeomorphisms between them. And so they kind of brute force classified all the possible little steps that exist between, like adding more and more space between every point.
Yeah. But I hope it kind of makes, like, I hope the first thing I said makes sense, where like the higher the the higher the number in the T, so like the higher up the list the separation property is, the more like separate or like further away 2 points are, right?
You want to give a visual example?
Sure.
With the whiteboard?
So let me know if I'm butchering the definition, but I believe the T1 axiom basically, let me annotate, basically says that like a space is like has a T1 property if for any 2 points you can draw an open neighborhood around one of them that doesn't contain the other, right?
Yeah, that's T0, no?
That's T1, I think.
So what's T0?
Oh,
I don't think
yeah,
there
no,
is
no, there
T0.
definitely is a T0, but I don't think he mentioned it in the lecture. I think it's something where, oh yeah, I know T0 is a lot weaker. I think it just says if you have 2 points, an open set around the first point won't contain the second point or
That's
something like that.
T1.
No?
T0 from Wikipedia is if you have 2 points, then there's an open set such that either one of them is in it and the other one isn't, or the other one is and one of them isn't.
Yeah.
Okay. And then T1 is like for both of them, you can draw, like you could do this, like it's both for T1.
Or maybe it's just one closed set. I don't
No,
know.
no, no.
Okay,
Like
so for T0, it's one or the other.
so for T1, it's both.
For T1, it's both, but not necessarily at the same time. Then for T2, it's both
And
and at
T2,
the
it's
same time.
T2, it's at the same time.
Right.
Now it just looks like.
What do you mean? What do you mean not at the same time though?
So okay,
Go on.
yeah. So let's clear all this stuff. Yeah. So T0, either you have this, or you have this. Okay.
Okay. Sure.
And then in T1 is both can happen.
Oh,
So
okay.
this,
Not necessarily.
and you
Okay,
can
of
have
course.
this, but not necessarily at the same time, right? And then T2 is at the same time.
Wait, but T1, can you have it at the same time or no?
No, because then you just consider it T2, right?
Then what's the difference between T1 and T0?
So okay, T0 is like if you have 2 points, then you can either draw this one, or you can draw or you can draw this one. Okay. And with T2, or sorry, with T1, you can draw this one and you can draw this one, but you can't draw them both at the same time such that they don't overlap.
Oh, okay. I see. Okay, that makes sense.
Yeah. And then
T1 is or
yeah, and then T2
okay.
is you can draw open neighborhoods around both that are disjoint.
Yeah. Oh, and then T3 is something like you can close, or you can draw closed neighborhood with an open neighborhood around one.
Yeah.
Interesting.
Yeah.
Okay,
and then
that's cool.
He said you have like T2.5, where it's you have 2 points and you can draw a closed neighborhood around one that doesn't contain the other one. Yeah, I wonder how many T's there actually are. How many separation properties?
Seems to go up to 6.
Okay.
Yeah. And there's also something called a normal topology, which is maybe similar to.
I think that's either 4, 5, or 6. I can't remember which.
Oh yeah, no, I think that was 4. But yeah. Okay, so we've done T1, T2, and how about this? What is so special about T2? Taman, you want to take this one?
What is so special about it?
Yeah.
Just what do you mean by special?
I mean, we seem not to care that much about T1 or T0 or T2.5. It's specifically T2 that we find very important.
Because it's similar to what we consider Euclidean space. Is that it? Or I'm not sure what you're trying to go for.
Yeah, okay, fair point. Okay, because I'm pretty sure if a topological space is Hausdorff and paracompact, then it has a really nice property of
the Heine-Borel.
No, that's metrisable.
Okay, so
I'm talking partition of unity. That's what it is. If a topological space is H2 is T2 and paracompact, then it will have a partition of unity.
What is a partition of unity?
Yeah, that was something that he just gave the definition. And I don't know the intuition for it. Yeah.
Okay, here, I'll go for the intuition. I think I found something neat.
Need to cover the compactness stuff first, though.
Oh, you think so?
Well, the definition relies on the. Okay, yeah, go for it.
I don't know. To me, the intuition is this beautiful graph here, which is that, like, if you imagine a circle, like I'm sure you've already seen with manifolds Wikipedia. The main example is that you have a circle. Yeah, you have a circle and you take 4 charts, right?
Yeah.
And so the idea behind a partition of unity is that for each of those charts, you assign it like an ownership value of how much it owns a specific point of the original manifold. And the reason you do this is so that integrals behave nicely. And when you're trying to take an integral of a specific chart and you're trying to assign like the resulting property to the space as a whole, you know how to do it properly. By using, like, this is why it's called like a partition, like you're partitioning every point of space. Here, it literally says it here. Every point of space will have a set of continuous functions where the sum of all those functions for that point is 1. So does this make sense intuitively, or should I go more into it?
No, it makes sense. I just don't see why you need the other conditions to be able to do so at all.
Like why H2 and ParaCompactness imply partition of unity. Okay, shit, yeah, I have no idea. That'd be something to have to walk through. But yeah. So this is like goodish intuition for this.
So yeah, I don't see why this is useful either.
Yeah. Well, the idea is that when you have a manifold, a very complicated one, you prefer to deal with the charts of the manifolds.
Okay.
But then some resulting properties from the charts are very difficult to generalize. One property that's easy to generalize is continuity. If you have a path that is continuous on a chart, you know that it's also continuous on the manifold. Like if I give you a globe and then I give you some charts of the globe and you're a sailor and you see your path being straight, you wouldn't expect the path on the globe itself to, hop around. Like it would be continuous as well. That's one property that's very easily extendable. Like it's even maybe not part of the definition of a manifold, I'm not sure. But if you were to take an integral on your chart, okay, here I'm talking a little bit of blah, 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 a little bit general. I don't have a specific example in mind, but if you were to take an integral and you wanted to generalize different properties surrounding that integral to the manifold as a whole.
What do you mean by different properties surrounding it?
Oof. Okay. So yeah, this is where I'm not exactly sure, because when I think of integrals, I think of integrals over a curve. But one thing with the multilinear algebra lecture 2 weeks ago is that I feel a lot of things can be integrals that I don't expect it to be, or maybe I'm just wrong with that. I don't know, maybe what would be an example? So let's say you have a chart with a curve on that chart. Okay, let's say you have 2 curves on a chart and you're finding the area between those 2 curves or something.
Okay.
And if you know something about charts, like charts of the Earth specifically, oh my God, I'm sure you've heard of this. It's the, what's the name of the map that we all use, or the chart of the Earth that we mainly use?
I don't remember the name.
Central projection, stereographic projection. So
yes, exactly that. But it has the name that starts with an M.
Mercator.
Yeah,
Mercator. Yes.
Yeah.
Exactly. And so Mercator has some it twists and turns what's going on the farther out you go, especially the north and south or whatever. So there would be errors in the charts, and you'd have to accommodate for those errors by using, I don't know, a partition of unity, somehow assigning different charts different priorities. Like if you had a chart that perfectly, where the 2 curves you're trying to measure are right in the middle of the chart, then that chart would have a very strong, like it would account for a lot of the value of the resulting integral or something. Okay, but this is all blah, blah, blah. Like this is the intuition, I feel. I haven't actually walked through a specific example. Which I probably should.
I think Mercator projection works.
Yeah, go ahead.
Do you guys know how the Mercator projection works? This is kind of a tangent. So
Yes.
you take a globe, right? Then you wrap a cylinder around it.
Cylinder,
Then you
yeah,
project the globe
project.
onto the cylinder. But
Yeah.
this is not good enough. This is just the cylindrical projection, because what happens when you project that way is you don't actually preserve area. So what Mercator does, it takes the resulting cylindrical projection and it stretches it up until area is preserved.
Interesting.
Oh, that's cool.
Wait, but does it stretch it uniformly, or does it stretch?
No, it's not.
The...
It stretches
Okay, I
along
see.
some logarithmic scale.
Okay,
Because
yes, I
at
was about
the-
to say, yeah.
Yeah, at the poles, you would need to stretch more because the poles onto a cylinder would be tiny when projected.
Yeah.
So
Mhm.
while all area is preserved on Mercator, distance isn't.
Okay,
Actually,
cool.
it's impossible to have a projection that preserves
Preserves
distance.
both. Yeah.
That's probably because of some fundamental math reason. Do you guys think that has to do with oh my god, the last topic in the list here? Does that have to do with fundamental groups?
Perhaps. There
I'm
are
sure you
what
could
you
come up with a proof.
there are things that you call conformal maps. So, for example, I can't remember it was the stereographic or central projection of the globe that does it, but it preserves angles. There are ones that preserve straight lines, and there are those that preserve area, but there's nothing that preserves distance itself.
Yeah,
Yeah.
I don't know if it has to do with the I don't know if it has to do with the fundamental group, because here we're more concerned with like distance and angle and area, whereas those things aren't of concern in like topology. Like you could have, just like a sheet of paper that's completely flat, and then you like twist it, and topologically it's exactly the same. Like you would have the same fundamental group and everything, even though you just twisted it.
Okay, yeah.
So it's probably has more to do with like, I guess, geometry.
Yeah. It's probably a different, well, I'm sure there's a part of math that addresses this, but
Yeah.
Topology and group theory is fundamental groups is group theory, correct? Yeah.
Yeah.
Yeah, I would say probably doesn't address it. But yeah, let's go on to the next one with covers, open covers, subcovers, and finite subcovers, and all the covers. Adar, you want to take this one?
Sure. So a cover of a space is just a set of, or a cover of a space X is just a set of subsets of that space that, or whose union is the entire space.
Does
And
it
then
have to be a space? Does a cover have
I guess
to
it could
cover-
just be a set. I guess it could just be a set. But then in the context of like topology, an open cover is a
Wait a sec.
cover. Yeah.
Are you sure it has to be a set? Because how, like, the cover has to cover things that are close to the original point. But how do you have a notion of closeness with just a set?
Hold up. I think we might just have to talk about topological spaces since we're leading up to compactness anyway.
Okay, sure.
So let's just say, maybe this isn't like the best definition, but let's just say a cover of a topological space is a hold up, let me just pull up the actual definition. But an open subcover of a space is just a collection of open sets whose union is the entire space. Okay, that much is for sure.
Which okay, so for open subcovers, for sure it has to be built on a topological space, because you need to have like your list of open sets.
Okay, so I just looked at the definition, and yeah, the subsets don't have to be neighborhoods. But then in an open covering, they obviously need to be neighborhoods.
Whoa. The subsets don't have to be neighborhoods? What do you mean?
In a cover of a space. So collection of subsets of a space cover the space if their union is the entire space, right?
Okay.
But then in an open covering, the additional requirement is that those subsets are open.
So essentially, you're telling me that you can have covers over sets, except it's really funny when it happens because it goes against a lot of intuition, or not that it goes against it. Because you're like, if I was to tell you that I'm building a cover over the set R, that's possible. Yeah, just a cover is possible. it's weird because yes, I am including all of the elements of R, but I'm not including them in a way that fulfills my intuition on closeness between different points in R.
Well, how does that come into this?
You just
I
have a
don't know.
set and then you're like putting blankets over it until it's completely covered.
Yeah, but the point is, what is a blanket without a notion of closeness or,
Well,
I mean,
You don't
continuity?
need one. It's just elements.
Yes, I
Yeah.
know. It's just unfortunate. I mean, I guess it's possible, but okay, sorry, tangent.
Maybe like an open cover satisfies your intuition a little more.
100%, yeah, open cover, because you
Um,
get blankets, like it actually makes sense. But sorry, yeah.
Yeah, what was the next bit? So yeah, we have open
Subcovers.
covers. So subcovers. So a subcover, I'm pretty sure, is just a subset of a cover that also covers the entire space.
For sure.
And then you could have like, and this is of interest in when defining compactness, finite subcovers.
Yeah.
So if you have like an open cover of a space, a finite subcover would be a finite subset of that open cover that also covers the entire space. And then, yeah, like compactness is basically defined in terms of like finite subcovers.
Okay. Oh, and do you want to do compact spaces? Or
Sure. I mean,
okay.
yeah, I don't
So
mind.
what's the intuition behind compactness then? Like I get the definition and how it works. And I could see how I could prove something is compact or not compact, but I don't see the picture I'm supposed to be having.
Yeah, that's like I can't say I have a good like intuition of it either. But the way I've heard it described is like if a space is compact, then in like some sense it's finite. And like this notion of finiteness doesn't have like an analog. So you can't, it's not like the same in like kind of finiteness as like, oh, this number is less than infinity. It's qualitatively different. But you know, like I said, I don't have like what I'm saying right now is like I think I heard Terry Tao describe it like this, but I can't say I have a good intuition of it myself. And then like if a space is not compact, then you know it is in some sense infinite. And like I guess one way or like one example that might aid your intuition is if you look at the open interval in the standard topology, like let's say from 0 to 1, that open interval is homeomorphic to all of R, which is, you know, like infinite. So yeah, that example alone doesn't, you know, explain much, but I guess it kind of like validates this, you know, sense that compactness is a kind of finiteness.
I mean,
So for example, all of RD would be, or I guess R to the n, that would be compact.
No,
it wouldn't.
It wouldn't. Why not?
Because you can't define a finite subcover of R, of RD. You can't define a finite subcover of it. Or there's no cover with a finite subcover.
Right, because all the open neighborhoods are balls and the radius of the balls are finite.
Yeah.
Yes, exactly.
Okay. But on the 0 to 1, the open interval from 0 to 1, then what about that? That still wouldn't be, or it would be? Yeah.
I think it would be, yeah.
No, well, because the two ends are open though, so you keep on approaching them, but you can't actually cover them.
Yeah.
Okay, but if it were the closed interval, that would be a different story.
I don't understand this part. What do you mean?
Right, because if I'm taking the open interval from 0 to 1, right, I can have an open set that's like 0.001 all the way up until 0.999. But there's still that 2 bits at the end that are
What
uncovered.
about having an open set from -1 to 0 or something?
Okay, if you
0.
went from
5.
like -1 to 2, which would technically, I guess, cover 0 to 1, but -1 to 2 wouldn't be in the topology, like the induced topology of the 0, 1.
You're right.
Wait, hold up, I'm confused.
Or does it?
What did you just say?
Right, so he's saying I'm making
saying-
a guess that the
yeah, go ahead,
open
yeah.
interval from 0 to 1 is not compact because you can't cover it in intervals. Jay is saying take the interval from -1 to 2. That's the open set in R, but it's not the open set on 0 to 1 though.
Yes, exactly.
So I'm not sure if that works or not.
It definitely, I think, yeah, no, I get your explanation.
But
Like, Adar, you understand? Or do you want me to?
no, wait, but Adar, is that something you can do or you cannot do?
No, I think you can't. The entire definition is that you have to get your open sets from a topology. What topology is it? The subset
It would be
topology.
a subset, yeah.
Yeah,
or
right.
subspace.
You can't take a topology that's outside
Okay,
of it.
but let's say I went with the closed interval, then what? Like the closed interval from 0 to 1, like what would you take that would cover it? Because
Yeah.
Well, no. Well, the point of the subset topology, or like the subset topology, is that it takes the intersection.
Okay, I think I might have gotten it, but yeah, go ahead, David.
Yeah. Like if I give you share screen whiteboard, if I give you a plane and then a line, and I'm trying to take the subset topology. No, wait. Yeah, I give you a hard line like this. So hard dots on the end.
Right.
I don't know, whatever, closed interval.
Yeah.
It's a hard. Yeah. So if you were to do this and you were to take the subset topology, you would have an open set that looks like this. Okay, I'm mirroring it here. Okay, like just pretend that it's actually drawn over here. So you would have an open set with like a closed endpoint, but it's still open because of the way that the subset topology is defined.
Right, because you take the intersection or something along those
lines.
Right? Yeah.
Intersection. So that's why you can still cover.
Okay, yeah, you can take another one and it works. And the endpoints don't matter because it's part of the topology because you intersection business. Yes. Okay, makes sense.
Exactly.
Cool.
Okay.
Also,
cool.
keep in mind. I think we might be thinking about this the wrong way. So even if we can find like finite, I think finite subcovers of like an open interval do exist, but the question is, does every open cover of the open interval have a finite subcover? And then there, the answer is no. So it's actually about finding counterexamples.
So
maybe give me to like give an example.
Can you give me proof? Yeah, go ahead.
Sure.
I'll share.
So let's just read off the definition of how do I get out of full screen for a sec? Okay, here.
Double click.
Let me read off the definition of compactness just so we're all on the same page. So a space X is compact if every open covering of X, like the space X, if every open covering of X contains a finite subcollection that also covers X, okay? So it's kind of different from looking for finite subcovers where what we're saying is every single open cover has to have a finite subcover. So if you can define even one open cover that doesn't have a finite subcover, then the space is not compact, right? And then the simplest example for 0 to 1 would be, is the whiteboard still open?
Oh, sorry.
Are you drawing something? Because I can't.
No, I'm not drawing anything yet.
Okay.
Now I'm gonna draw stuff.
Yeah, no, if you want to do me a favor, how is the real line, how can that be covered with finite subcovers?
I don't think it can.
I don't think it can,
so.
but the open interval 0 to 1 does have finite open covers, I believe.
Really?
Yeah. Wow. So like one example would be 0 to 0.5.
Interesting.
0.4. 1. That would be an open finite subcover or open finite cover of 0 to 1.
Oh yeah, we can do that.
Yeah.
Right.
But so that's why like the definition says that every single open cover has to have a finite subcover. So now let's define an open cover of -1. Actually, let's just define one from 0 to 1. Let's define an open cover of 0 to 1 that does not have an open, or that does not have a finite subcover. And we'll define it like this.
Oh, right, because as long as you can find one where it doesn't work, then it doesn't work, period. Right.
Yeah, exactly. I'm trying to think of how to define it now.
Yeah, actually, how would you construct?
It's definitely possible. I can't
What do you
think of
mean?
it right now.
No, okay, so what if you were to take, let me think.
You need some sort of asymptote. That's the like main thing.
Right, no, this is completely doable. So take the open set 0, then do the, okay, I can draw 2, right? Yeah.
Yep.
That's right. Okay, 1 second. Let me get this up.
I'm looking forward to this proof. I have no idea how you will manage to do this. Oh, because
let me think this one through.
wait, what if you just did something dumb like this? 0 to 1.
Yeah, that would work. That would work.
Which one? This one?
Yeah, that would
Oh.
work.
Wait,
Yes.
Can you explain to me this one here?
That I mean, like,
Yeah,
I'm not sure what
okay,
that
so-
is.
The problem is, okay, so every single cover we come up with, we must find a finite subcover. So for example, the one that you gave, David, that is a finite subcover already, so it's good. So now, to prove that it is not compact, we need to find just one infinite subcover, one infinite cover, such that it does not have a finite subcover.
Okay.
Like we find an infinite collection of blankets such that there
Sure.
isn't a finite collection of blankets within it. And I am claiming that this one is that infinite collection of blankets. We're looking for.
Yeah. It
Let me
is.
see this.
I think that just
Okay.
works. Huh?
Yeah,
No,
it
wait,
definitely
no,
works.
wait, 1 second. That
It
should
just-
not be. That should
It
be.
should be
I.
infinity, and also it should be from 1 to infinity, not 1 to. Oh, actually, no, you did say that n is
Yeah.
infinite. Okay.
I
Whoa,
could've-
whoa. Okay, I am fully lost. Why I?
So this
I-
would be.
Yeah.
This would give you the set. It would give you the set 0, 1/2, then 0, 3/4, right? Then 0, 7/8, then 0,
Yeah,
15/16, then 0, 31/32,
Oh, cool.
then 63/64, and it approaches 1. So
Yeah.
at infinity, we say like it covers
Yes.
all of it. But if the moment you take away one, like you cannot, there isn't a finite amount of
Yeah.
them
Yeah.
that can cover it, because every single. Actually,
Yeah.
I guess you could say like the one at the very limit, except there is nothing. Wait, does this? Yeah, wait. Can you even say this covers it? I guess you could. But
No, you can say it covers it, because for any point in X, you can find, like, in any point from 0 to 1 open, you can find like an open set in this cover that contains that point.
and then for every finite one that you give me, I just find the cover with the maximum n. Then I find in a point that's past that cover.
Yeah.
Because there's going to be a tiny sliver left that I can take points from.
Yeah, exactly.
What does it mean to converge here, though? Because
Yeah.
you haven't have you defined the topology? Oh yeah, you have. But what if you give me or if I give you a dumb topology, like the discrete topology?
I like.
We're just on R, and then we just we just made a sequence of increasingly large subsets. And then, as Adar said, any point that you give within 0, 1, I can give you a cover that contains it. I just take n to be big enough.
No, I see. It makes sense to me. I'm just curious if there's something that is breaking here. I don't think so.
I don't think so either.
Yeah, no, this seems right. And then, like, I guess the more difficult thing is proving that something is compact, because it's not just a matter of finding a counterexample. You have to
It's proving all of them. Yeah.
Yeah.
It's very annoying.
Like even like I was looking at the proof of compactness for the closed interval on the real line like a little bit ago, and like, you know, it's not as simple as this. That's for sure.
So does this mean that the interval 0 to 1 is not compact?
Yeah, it's not compact.
Can we search that up?
Sure, go ahead. But yeah, we've just defined here an open cover of 0 to 1 that does not contain a finite subcover.
So how wrong is my current intuition where I guess a topology is compact if every single one of its bounds, like whether it's upper or lower in any dimension, is contained within itself?
Can you restate that?
So like for example, this set
No,
here,
can you restate the explanation? I was reading something else. Sorry, I was reading the example.
I'll try to. So like, say I take this set, it has the it had like a from 0 to 1 has one dimension, right? Like it's just the real a part of the real line, and its least upper bound is 0, and its greatest lower bound. No, its least upper bound is 1, and its greatest lower bound is 0. But both of them are not within like the set, like the interval itself. So how wrong would it be to say that every single compact set in the compact topology, in all of its dimensions, all of its greatest lower bounds and least upper bounds are within itself, and that's what makes it compact? Does that work?
No. What if you take a torus or something, or something that wraps on itself?
That's basically like what you said is basically like the Heine-Borel theorem, I'm pretty sure. But that doesn't apply to like arbitrary topological spaces.
Just to Rn,
yeah. The Heine-Borel theorem basically says that in Rn, and I believe maybe arbitrary metric spaces, but don't take
Heine-Borel, it defines a metric over it though. I don't think you need a metric. You just need some ordering, right, of the elements.
But even if you define an ordering, like you could still define topologies where that ordering, you know, is meaningless. Yeah, so like I don't think that, like, also like what you said kind of relies on a notion of dimension, and we can't, you know,
that's true.
We can't assume that we have that either.
Yeah. So I searched up if 0, 1 is compact, and it says it is not compact.
Yeah.
Is that 0 is a limit point of the set, but is not in the set. Yeah, so it has no finite subcover because of that limit point. Very
How are we going to get through the rest of this in 4 minutes?
Oh boy. Yeah. When do you guys have to go?
I'm going to head off at 45, or I could probably stretch it until 50, but I do have something right after this.
Okay.
So I do have to head off.
So let's do ParaCompactness just very briefly, and then go right into, I don't know. Yeah, this is
yeah. I know about this one.
We could briefly talk about fundamental groups. I mean,
yeah, can we do that? I'd like to hear your perspective, both of your guys' perspective on this, because it's new to me.
So you want to do that instead of ParaCompactness? Because
yeah, I already understand ParaCompactness.
Okay,
relatively.
sure. So the fundamental group is basically a way to classify spaces by looking at loops over those spaces. A loop is just like a path, like a line, like a path in a. Let me just draw and it'll be clear.
Yeah. Whiteboard.
Yeah. Okay. So here, annotate. Yeah. So we have like some sort of space. We have like a sphere or torus, or maybe a double torus. Okay, whatever. So we have like some sort of space like this, and we want to find a way to like count the number of holes in that space. And when I say holes here, I'm talking about holes of like a specific like kind of like dimension, I guess.
Yeah.
So basically, if you draw like if you draw like some sort of path on a sphere, and you can draw like another path on the sphere, or maybe you could draw one that goes all the way around, like this one that we have here.
They're all homomorphic to each other, or is that the right word?
Well, they're all homotopic to each other.
Okay. What's the difference?
Don't worry about it for now. It'll just take a little while to explain. The intuition here is that if I take this path, I can, like, you can imagine like kind of wiggling it around until it becomes this path, right? You just literally just move it continuously across the surface of a sphere, right?
Oh yeah, but over here you can't do the same thing because you wrap it around like this, but then around.
Right, like that. And that you can't just wiggle its way to this, and you can't wiggle its way to this.
Oh yeah. Oh, and there's also this example. Okay, let me see if I understand this. This is one that was in the lecture that I kind of moved my mind a bit. So if you wrap it around in this direction, this is a cylinder that goes on forever. I think this would be S times R or something.
Yeah.
So if you go it this way, you can't actually wiggle it around to this way. And so then there's something about how this is similar to Z, because you can wrap it around 0 times, 1 forward, 2 forwards, 3 forwards, or 1 backwards, 2 backwards, 3 backwards.
Yeah, it is. That's maybe like I guess this is just an easier way to visualize the fundamental group of a circle. So it's just easier to visualize because you can see the number of loops like separately, whereas here on a circle they just kind of like overlap when you try to visualize it. But it's the same idea. You're right. Like
there's a really nice one too when you're talking about path induction and based path induction, which is completely irrelevant here, but like there's a nice picture from that's in 2D. So if you have a disk like so this is just your circle on a flat plane, but this circle has like a little hole at the origin. Then you can imagine like if you start a point here, then you have a loop path like this, but you can also have a loop path that goes around the hole. And there's no way that you can get the one that goes around the hole to not go around the hole anymore.
Yeah. So I get this idea with paths, but how does this relate to groups? Because I'm pretty sure a group is a set equipped with a blob or a glob or whatever it's called. An operation. I don't know. That's what he calls it. With something. Whatever that something is
with an
called.
operation that satisfies like certain axioms, right?
Which I choose to call glob or blob, or I don't know.
Okay, sure. So
So my question is, what does that have to do with this? Yeah.
Can you guys clear your?
Oh yeah. It shall be cleared.
Yeah. Let's start with the fundamental group of a circle, which is actually the same as the fundamental group on the cylinder that you brought up, the infinite cylinder. So first of all, is it clear like what a group is, and is it clear rather why like the integers are a group?
Well, with addition, then yeah, it's clear.
Sure. So let's just say like a group G, like a pair, like a ordered, I don't know, like a tuple G in operation plus is a group if plus satisfies associativity. I just butchered this, but yeah, okay, whatever. Plus is associative. And what are the other ones? Tanim, you wanna help me out here? I kind of forgot.
Isn't it or something? But then without the C in this case. I don't know.
There's a neutral element E. So okay, here it's just 3 things. So yeah, plus is associative. There's a neutral element E such that for any G in G, E plus G equals G plus E equals G. So just you can think of it as like 0. Like 0 plus anything equals 0. Anything plus 0 equals, anything plus 0 equals that thing, and 0 plus anything equals that thing. And then, yeah, so like identity element or neutral element, associativity, and inverse. So that for every element in G, there's another element in G where if you add them together, you get the neutral element. Okay, those are the three like axioms. So if we look at the integers,
Yeah, it's
we
clear
see
that
that
they're a group.
it's clear, like, yeah, 0 plus anything equals that thing, and everything has an inverse, and the plus operation is associative. So now we look at the circle, and we look at the paths on that circle, and we think like, what operation can we like define on these like loops rather? What operation can we define?
Oh, and that's the, okay, I see.
That
I see.
Yeah, that kind of would let us, you know, define like a group structure on these
Okay.
like on these loops. And the answer is like loop composition. So you take one loop,
Yeah.
and then to compose it with another loop, let's say like my other loop is this. So in total, if I like combine these, I get this. Like I'm drawing it really badly just because it's like it should be represented in 3 dimensions, and I'm trying to draw it in 2 dimensions. But just think of it as like,
one then the other.
Yeah, like I'm going around, and then like let's say the direction on this, hold up. Let's say the direction on this is this way, and the direction on this loop is the other way. Then if I first go this way, and then I go this way, what do I get? I didn't actually go anywhere, and my loop can actually, like if I'm drawing this over a circle, if I first go this way, and then I go back this way, then I can actually like get rid of the entire loop. I can like continuously wiggle the loop around to a point, because it's not actually being constrained by the circle, if that makes sense.
I might have to do some more research on my own for that, which is
like here. Let me maybe draw. So you start with this thing here, and then you have let's see, 1, 2. Then you have like this. Like you see how I kind of moved the path a little lower down.
Mm-hmm.
And then you like slowly move the part that I'm circling in green. You slowly move it closer and closer and closer, and you reduce the entire, like you shrink the entire loop until eventually you're left with like this. And then you can shrink it down even more until you get to a point, if that makes sense.
Okay. I'm not sure why you would do that, but we are sort of out of time. Taman, if you want to go, I don't know.
All right, I'll see you guys next.